Good afternoon, everybody. Welcome to our webinar about the advanced preparation methods of TEM samples. First, I'd like to thank you very much for being here, because it's so nice to see the great number of the participants. It's a good feeling. Thank you for that. My name is András Szigeti. I'm the CEO of Technoorg Linda Company. I will be your host today. And let me introduce my colleague, Dr. György Zoltán Radnóci, who will be our main presenter for today.
Good afternoon.
György is a scientist, a physicist, and also an electron microscopist who specialized for the TEM applications, which is very useful for today because he can show us some very nice examples about the TEM preparation and the result, what we can achieve, right? So that will be the main topic. But before starting that part, that we see what you can expect for today. The whole session is about 60 minutes. The presentation part will take about 45 to 50 minutes, and then we will have a short session for answering your questions. But please feel free to raise your questions during the webinar anytime. You can use the chat option in the software, and our colleagues will do their best to answer your questions continuously. And at the end, we will have the chance to pick some of those questions and answer them publicly. Don't worry if we have no time for all the questions, because in the follow-up emails, everybody will get the whole list of the questions and the proper answer for those. So what we will talk about today. Our goal is to give you a broad picture about the possibilities of the technology and the fields where it can be used and where it is useful. But obviously the main part, the deep part, will be the TEM sample preparation, where György will show you the examples. Let's start with the very first question: why we should prepare our samples? Obviously, because they are not good enough without any kind of preparation. It means the structure is not visible, and we cannot see all those details what we are looking for. So usually we start this kind of process with the mechanical part. So we cut those samples if it's necessary, and usually we polish them mechanically. So after the polishing method, the mechanical polishing method, we have a structure like this. On the top of the sample, we have a thin amorphous layer, what can absolutely disturb the image, what we would like to make. And once we remove this amorphous, we still have usually a destroyed, it can be quite thick actually, a destroyed and modified layer, modified by the mechanical polishment itself. So you can destroy and reorient your crystals, but what is covering the real structure, what you are looking for, and more dangerously, it can give you a false result. So you might think that this is the result what you are looking for, and the real structure of the sample, but it's not. It is an artifact caused by the mechanical preparation. So something is needed, an approach, a technique, what can remove everything, including the damaged and reoriented part, and gentle enough to keep the original structure as it was before. How important this kind of topic, we know that because actually we are focusing all our energies since we have been founded in 1990. So we don't have, by the way, hundreds of machines in our portfolio. We are focusing on this topic, producing ion mills, and we are deeply involved in all of the problems and difficulties you might face with. So, so actually this kind of sample preparation can be the missing part from the workflow. Well, when you have all the nice microscopes and everything, but somehow you realize that the final result is not good enough. Thanks to the decades of experiences and the continuous work in the R&D, for nowadays we do have dedicated machines and configurations for all kind of needs, because they can be different, even if the main principle, the theory behind that, those are same or very similar, but the technical approach, how we solve these technical problems, can be very, very different. So basically, in all fields of electron microscopy, the ion milling technique is commonly used because this is the gentle enough approach what can help you to achieve the ultimate goals. We will talk about the TEM samples, including the fib lamellas in details, and George will show us how to handle them. But first, let's have a broad picture and let's see what we can do with the SEM samples. Basically, you can have two different approaches. One is cleaning the original surfaces of the samples. The second one is cutting. So you tilt your sample and make a new cut, basically make a new fresh surface by removing some material and evaluate the inner part of the samples. In both cases, as you see, just right after the preparation, the ion milling, the surface is super clean, all the details are visible, the grain structure and everything is ultimately visible and clean. Why is that? Because we remove not just the unnecessary material, but also all the resputtered material, any kind of artifacts are avoided in these cases. You see some EBSD pictures on the screen. It's not because it is so important for everybody, but usually we use this technique for evaluating the cleanness, the quality of the freshly cut or polished surface. Why? Because it's very sensitive. So in case of EBSD, you get your information from the very top part of the material. It means 50 to 100 nanometers maximum. So if it's amorphous or dirty or destroyed, it will disturb your imaging immediately. So what you can see here, this is a highly prepared, after a very fine mechanical preparation. In some materials, you may have good results after a good mechanical preparation, but it's a material dependent method and very time consuming. So even if it's possible in some cases, it's better to avoid the ultimate mechanical preparation. But after a good quality preparation, usually you have this, basically nothing, no orientation map. And in case of soft materials, usually just some minutes or 10-15 minutes is enough to remove from the surface, you remove the amorphous and the destroyed layers completely and get these kind of images. This is the case in super hard materials like martensitic steel as well, so absolutely possible to achieve the top quality. Naturally, the preparation time is a little bit longer because these materials are a little bit more hard to sputter, but within an hour, if I'm correct, this kind of martensitic steel was prepared for maybe 45 or 50 minutes. So less than an hour, you can have the ultimate result without any kind of problem. So basically, this is what you can achieve on SEM samples. This technique is very popular for many applications, including the semiconductor and electronics industry, but also the failure analysis, and many others use this technique day to day. So it's a commonly used technology, but the most delicate and sensitive part of the sample preparation is definitely when you want to see the artifact and damage-free atomic structure. Actually, what you see on the screen right now. This is a quite famous sample. It was prepared on the Berkeley University in California in 1999. And why is it so important? First, because it was prepared with our machine, the IV4. That was the first ion mill what contained a dedicated low energy ion source on the market. And why it was so important? Because that was the very first chance to remove all those amorphous and destroyed layers caused by the mechanical preparation or even caused by the high energy argon ions, what covered this kind of detailed structure. So actually, from that moment, it was a new possibility which was given to the scientists to evaluate the completely amorphous and damage-free atomic structures. Basically a new era. So yeah, this is the world of TEM samples, and I will ask my colleague to continue and show us some details and nice examples how and what we can do.
Yeah, thank you, Andres. As Andres told you, I'm going to show you the way of preparing perfect or nearly perfect samples. And he also told you that I'm a researcher, so I've been the user of ion mills and related tools for now about 20 years. So first, let's see how we can get thin sections from bulk. Obviously, one way is cutting the sample with a microtome or pulverizing it to small pieces to get electron transparent regions. But we are going to talk about thinning today, that is eroding the sample surface until it gets very, very thin. You can do it mechanically, even down to atomic resolution samples, or you can do it chemically. But we are further talking about ion beam techniques, which can be either focused ion beam. Most commonly it is a focused gallium ion beam, and a broad argon ion beam technique that's called argon ion milling. In both of these cases, FIB and argon ion milling, we usually end up with the damaged surface. The ion beam, whether gallium or argon, is damaging or amorphizing the surface. So the next step for a perfect sample is argon ion cleaning, which means that we are flooding the surface with low energy ions and cleaning away all the damaged surface layers. So just in the beginning, let's compare the two commonly known ion beam techniques for thin sample preparation. The first big difference you will notice when you are actually at the time when you are trying to set up the laboratory for sample preparation, that for FIB you will need a complex and expensive machine, while for argon ion milling there is a simple and affordable machine available. The workforce accordingly is a highly trained technician for at least for the FIB, and the technician is enough for running the argon ion mills. On the preparation time and site specificity, the FIB is definitely better than argon ion milling. But if we look at the useful area produced by these methods, we see that the argon ion milling is producing way larger electron transparent regions on the sample than the FIB. Sample contamination is a very important issue. In the FIB process, you will have a fairly good chance to contaminate your sample with gallium and platinum. While in the argon milling case, argon will not likely stick to the sample as it is a noble gas, so very, very little amounts of argon can be measured on the TEM samples prepared by argon ion mills. And titanium and carbon are common contaminants in the ion milling process, but they can be avoided with proper ion mill settings. Sample heat load is also an issue. In FIB, normally it's acceptable. In the argon ion milling case, sometimes it becomes too much, and then cooled sample stages are used to avoid excessive heat load on the sample. Now, what are the advantages of argon ion milling? So, in my view, one main advantage is that we get gallium-free samples. So we don't have chemical reactions or visible contamination of gallium in the sample. The cost advantage is quite an obvious one, and it's quite a big advantage. Also in today's ion mills, if you need the ion milling and ion cleaning is integrated in one machine, ion mills are easy to learn, and they are easy to run or easy to use, and they are also quite robust compared to a FIB system, which needs much more attention, and sometimes you need to be really careful working with them. So let's have a look at the argon ion milling in detail. So the end result for a TEM sample should be it should be thin, depending on the experiment type, but it should be between 5 and 500 nanometers usually. It should be mechanically stable, and the shape should be a 3 millimeter disc, which fits the sample holder of a microscope. It should be free from artifacts, and it should be clean and smooth. So that's what we need. More specifically, that's how a TEM sample looks when it's ready after ion milling. So we have a titanium disc, and the sample is embedded in the middle of the disc. There is a small hole in the middle of the sample material, and the edge of the hole will be thin enough for electron transparency. The thickness of the titanium disc after ion milling should be no less than about 20 microns and no more than 150 microns. Yeah, and that's what we need. To achieve that, we will need a very gentle way to remove material. We will need accurate sample positioning or accurate movement of the sample, and very importantly, we will need safe procedures for thin samples. You can imagine that it's very, very easy to break a 3 millimeter disc, which is like the thickness is half the human hair's thickness. Technoorg's solution for this is programmable ion mills with 1 or 2 ion guns. Technoorg also developed a number of sample holders for different purposes, and the complete range of materials and tools for safe and repeatable mechanical preparation and sample handling. Now, these are the 2 ion mills offered by Technoorg for this types of TEM work. The Unimill is an ion mill that is capable of milling samples from the bulk material down to the thicknesses desired for electron transparency, and it also has a low energy ion gun for ion cleaning the sample. And the other machine is a dedicated low energy ion mill for dedicated ion cleaning. Mainly it's offered for FIB samples, but you can also use it for argon ion milled samples.
Let me shortly interrupt just for
Yes.
a second, because it's very important to understand and make clear what's the main difference between this kind of devices or configurations, because as you mentioned, there are 2 ways of preparing these TEM samples. One is having a bulk material and finish the whole procedure. This way has certain advantages, not just the cost but many others. The other one is using a focused ion beam to cut out a lamella, but even that way, this kind of final treatment, the final cleaning with low energy ions, is very useful. It gives a significant step forward by removing the gallium, by making that lamella amorphous, free and thin enough. So both cases, this is a kind of necessary step, the final cleaning. But furthermore, all the customers or the users, I would say, they are not looking for devices, this or that kind of devices, but solutions. So that's why the way how we try to develop our machines is offering a complete workflow with all kind of necessary devices and very modular configuration, so you can choose between the ion sources or have the right kind of cooling units or any kind of sample holder, what is really needed for your specific application. So in that way, we are talking about more like a solution, not just different kind of devices. So this kind of workflow, the recipes, the knowledge, and everything is a part of the topic and the offer, basically. Sorry for interrupting.
Yeah, thank you for this addition. Let's go on and look at Unimill in a bit more detail and how to use it. So Unimill, as I told you, has 2 guns. One high energy ion gun, which works between 2 and 16 kilovolts for fast milling of almost any material. And it also has a low energy gun integrated, which works from 100 volt to 2000 volts. Various sample holders are offered to this machine. There is an optional cooling stage for heat sensitive material, and the user interface is quite an easy to use interface. There is also a perforation detector for accurate interruption of the thinning at the right moment. And I should also mention that there is extensive support for special applications and samples. Okay, and here is how we start a preparation. So first, we should decide in which orientation we want to see our sample in the TEM. If we imagine this brick with the top side as a thin film, then this section on this picture would be a cross section. This one would be a traditional plan view, and you can also mill the upper and lower part with the ions, and then you will end up with a plain view from a buried interface or something like that. To cut the small pieces of the material, Technoorg offers a very advanced cutting tool. Actually, it is a small diamond saw called micro saw. It is designed for precise sectioning of small pieces. I mean by that, small pieces like 0.5 millimeter maybe, or 1 millimeter. The small pieces which will fit into the titanium grid during the preparation process. It is very important that this tool is designed to be used under an optical microscope. So you can closely follow the procedure of sample sectioning with the microscope. Of course, you can adjust the cutting force and cutting speed of this small diamond saw. Now, once you cut your samples, you will insert them into a titanium grid. For cross-section and plan view, Technoorg offers two different titanium grids. And once you inserted the sample pieces into the titanium discs, the gaps need to be filled with a special embedding glue. Now, the glue Technoorg recommends is the 81 glue, which is conductive, it withstands heat and solvents, and also a small heating stage is offered for the job. This heating stage can be also used under a microscope, and you can set the temperature of this heating stage between room temperature and 180 degrees very accurately. So you can use this for embedding the samples with the glue, and also for curing the glue at elevated temperatures. Now, the next step after embedding the sample would be mechanical grinding. It is very important that not only devices are offered, but there is a complete workflow with all the materials and tools needed for a repeatable and reliable procedure.
Another very important point here, just to make it clear. So you can find countless saws and polisher machines on the market. Really a big amount of them, but we are talking about very, very small samples. All of you know that the diameter is 3 millimeter, and usually once you use a titanium disc, the sample is even smaller. So cutting these samples with such a large saw, or using those extremely large polishing machines, it's just basically they are useless for this kind of job. So that's why we designed dedicated machines for this kind of delicate work, and this is the reason we call them small tools like micro saw, micro heat, and micro pole. They were designed for TEM samples, and as you mentioned, you can use these machines under a stereo microscope in order to see the details and finish the job in a very, very precise way. So yeah, it's a dedicated workflow for the preparation part of the TEM sample preparation.
Yeah, thank you for the addition. Yeah, as Anders told you, so these devices are really optimized for the 3 millimeter discs, which are used in the TEM sample preparation. I should mention one more thing about micropole, the polishing machine. The flat grinding cup or grinding surface for this machine is quite obvious. You can use it for making flat surfaces, but there is also a spherical grinding cup for this machine, which helps you to obtain concave sample surfaces. So you will end up with a disc a bit thinner at the center than at the outer edge. This will give you a sample which is thinner but still stable. This will help decreasing ion milling times and also maintain stability. When the sample is milled for long times, it will help you preserve the titanium disc at the edges. That's very important to maintain the sample stability. Now, these grinding surfaces can be rougher, or you can also do the polishing with this machine. Once you finish the mechanical preparation, the next step will be ion milling. In the Unimill setup, you have two ion guns in opposite position, and you have the sample in the middle. And you can position the sample either for the high energy gun or the low energy gun. So first you start with the high energy gun and ion mill the sample from both sides until you get a hole in the middle. But for this process you might need various sample holders depending on what kind of sample you are ion milling. Now Technoorg offers 3 types of sample holders for Unimill. The first one is a single-sided cooled sample holder for heat-sensitive material. Cooling means liquid nitrogen cooling, and this holder is a glue-mounted holder, so you glue your sample onto this holder for good heat conduction. It allows very low excess angles, but the gluing requires also a bit of skill. For a simpler process, you can use the double-sided holder. It's very quick because you don't need to turn over the sample while you are ion milling, so it's used for quick and automated milling mostly. And there is also a single-sided clamped holder, where a clamp is holding your sample in the holder. In my opinion, this is the safest holder, so you can use it for very safe preparation, and in the same time very low milling angles are permitted in this holder. So these are the 3 holders you can use. Now let's have a look at the user interface. So Unimill can be used in either manual or automated operation modes. In manual mode, you have total control and direct control over all gun parameters, all sample movement and positioning parameters. You also have a CCD camera, which is showing a magnified image of your sample, so you can closely follow the thinning process and sample surface evolution. In manual mode, you can either ask the system to maintain a constant ion current, or you can even use the needle valve yourself to regulate the ion current. But I think in most cases you will use the automated operation. So in this mode you will specify steps. Each step will have its own time and the parameters set for the ion milling, gun parameters and sample positioning. So you define all the steps you want to run on the sample, and then you just run the program and the ion will make the job. It is very important that for both manual and automated operation there is a perforation detector that works obviously for optically non-transparent samples, but for those it is very useful because it will stop the thinning process at the moment when you have a perforation. The perforation detector has a number of parameters which you can set. So if you already have a larger hole but you are expecting more small holes to develop, you can set the number of holes, what you expect. You can also stop the thinning before the sample is perforated if the sample, like silicon, gets a bit transparent while it gets thinner. So it is a very advanced and a very useful feature of the ion mill. Now, if you are ion milling, you are encountering common artifacts. Some of those can be avoided and some of those needs to be dealt with. So heating is and the resulting structural changes, that's a very common artifact in argon ion milling. To avoid that, you probably will use a cooling stage. Technoorg offers a cooling stage cooled by liquid nitrogen. So if you use that in combination with decreased beam powers, you will be able to prepare heat sensitive samples. Redeposition is also a common issue, but you can avoid that with accurate alignments, and if you keep the hole on the sample very small, that usually helps you to avoid titanium redeposition. Surface roughening is also an issue, but if you keep the milling angle low, that will not be disturbing for most of the samples. The single-sided holders allow practically down to zero milling angles, and normally we recommend to use them around 5 degrees, and then surface roughening for most materials will not be an issue. The last point here is surface amorphization, and this will surely occur with a high energy ion gun, and the only way to get rid of this problem is to use low energy ion cleaning, either by fib or conventional argon ion milling. You will get this type of artifact, and especially for thin samples it is very disturbing and it needs to be removed. Let me show you an example. This is an argon ion milled diamond piece, and you see on the left image how the sample looks when the ion milling is finished at 3 kilovolts with a high energy gun. So on the lower part of the image you see some lattice of the diamond, but obviously this sample cannot be used for a proper investigation. Now, if you clean this sample with 500 volt argon ions, you will notice that the lattice image looks much better. But let me show you. Oops, I need to go back one. Thanks. Where is my mouse? Yeah, there it is. So you see that there is still an amorphous band at the edge of the sample. So it indicates that we still have some amorphous material on this sample. But if you look at the right image, which shows the sample when it was cleaned with 300 volt argon ions, you only see a very, very little amorphous edge, and the lattice image here, it looks much, much better. Let me show you the next example. This is a piece of aluminium oxide. The image on the left is a raw fib cut lamella finished at 16 kilovolts, and you see that there is some lattice in it, but you're not really able to evaluate it. It's dirty. It contains a lot of amorphous artifact. So this is not what we want. The right image shows the same sample cleaned with 300 volt argon ions, and you see it's a crystal clear image. Really, I will talk about this a bit later. So the machine to do this process, the dedicated machine is gentle mill. Of course, the unimill also has a low energy ion gun integrated, so you can do it with that as well. But this is the dedicated machine for this job, with a low energy gun operating from 100 volt to 2000 volt. It has an easy to use user interface, almost the same as in the case of unimill. And it has double-sided sample holders, as in this case we do not need to worry about heat load on the samples. The low energy ion beam creates very, very small amount of heat on the samples. I told you we have double-sided sample holders for this machine. This is for easy and quick operation. We have two types of sample holders. One designed for a disc shape sample. This is for argon ion milled samples. And there is also another sample holder which is optimized for fib lift out grids and very small pieces of samples mounted on those fib lift out grids. Now let me show you some examples how the samples look after cleaning in gentle mill. So this is an overview image of a fib lamella. On the upper edge you see the protecting platinum layer, which is black, and marked with arrows you see the difference between this protecting platinum layer before and after the argon ion cleaning. You see that the sample shape is mostly preserved. Only a little amount of platinum was cleaned away in the argon ion cleaning process. But then, and when we look at the higher magnification images, big differences are seen. So on the left image we see the raw fib cut lamella finished at 30 kilovolts, and you see a wide amorphous band on the sample edge. Also in the lattice image to the left from the amorphous band, there is some cloudy contrast, some unevenness of this lattice image. On the right side you see the cleaned fib lamella. You see that the amorphous band is practically cleaned away. There is only a very little part of it remaining. I will show you it later. And also, if you look at the lattice image, it looks more uniform than in the case of the raw fib cut lamella. If we look at even higher magnifications, on the left you see the border of the crystalline and amorphous region, and here just have a look at the crystalline part with its unevenness and noisiness. If you look at the right image, you see that only a very, very little amorphous band is seen on this, and the crystalline part is completely uniform. So it looks much better than the other image. I should also mention that the small amorphous part is not because we didn't clean the sample completely. As we clean the sample, it will be completely clean, but when we remove it from the ion mill, then it encounters atmospheric air while we are transporting it to the transmission electron microscope. and silicon will form a native oxide on its surface, which will be about 2 nanometer in thickness. So on both sides of this thin section, we will have 2 nanometers of silicon dioxide, and that's what we see on the edge. But from the lattice image, I think you can judge that this sample was cleaned properly and it is as good as it can be. Now let me show you another example. This is gallium nitride. Or aluminium nitride on a gallium nitride substrate. The thick part, let me show you this thick part is gallium nitride, and we have a very, very thin aluminium nitride layer on it. Also, please look at this small droplet. This is a gallium droplet. We commonly have gallium droplets after FIB processes on gallium nitride. This is because of selective sputtering. And on the right, you see the cleaned argon ion cleaned lamella. You see that the lamella got much thinner. It's obvious from these images, but the shape is more or less preserved. The gallium droplet was also cleaned, so we don't have this disturbing artifact anymore. And if I show you the high resolution images, on the row lamella actually finished at 2 kV. You don't see much amorphous band here. This is almost all crystalline, but the quality is not really good, partly because of the thickness, but also because of the damaged crystal layers on this sample. The aluminium nitride layer is visible here, but its structure is not really revealed. Now if you look at the other image with the cleaned sample, first I like to point out this region. So you see it is full of small platinum particles. The size of the platinum particles here, if you compare it to the micron bar, which is 20 nanometers, then you can estimate the size of the platinum particles to like 5-10 nanometers, and they are not overlapping. It's very important. So that not overlapping like they are overlapping in the. Oh, where is my mouse? Sorry. Yeah. So here, a lot of platinum particles are overlapping in the TEM image. Here we have them just next to each other. So this indicates that the sample thickness is down to about 5-10 nanometers, which is very important. This demonstrates that we can reach such very small thicknesses and still maintain sample stability. Also, if you look at the lattice image, which gets very, very weak actually when you get a thin sample, but maybe you can lean closer to your screens and have a look at the lattice image. That is a very good quality lattice image. You can see separate aluminum nitride columns. You will, if you look carefully, you will also see some dislocations within the gallium nitride. Now let me show you again the first example I showed you. So this is aluminium oxide, and now you will understand why we don't have any amorphous band here. So this was perfectly cleaned. Aluminium oxide is already an oxide, so it will not form additional amorphous oxide on air. So here, as this is a wedge, you see this material slowly disappearing in vacuum. Here is the edge of the sample where the contrast of the lattice is already very weak, but still you see the lattice image at the very edge of the sample. And with this I give the stage back to Andras. Thank you very much.
Thank you, George. It was, I believe it was not just an interesting but very useful presentation for all of us. So now the Q&A session will come, but before that I'd like to give you some basic information. One is that after the webinar, within an hour, we would send out a very short survey. I kindly ask you to fill it out and send it back, because it's just 2 or 3 minutes for you, but a very, very important information to us, because we are interested in some points, like which kind of topics you are interested in and how we could improve our activities and our events in order to give them more and more useful information and more useful data. So please help us and help us to help you, basically. Also, you will receive some follow-up emails with some contents, like the video recording of the webinar itself, so you can review it anytime, or you can distribute it if you wish. Also, I would point it out that there is a possibility of having a little bit deeper consultation with us, so that would give us the possibility to have 30 or 60 minutes or even more, just to see your exact difficulties or your application, your day-to-day problems. Who knows, maybe we have some kind of solution for those. So please feel free to contact either us or our local partner, Summer Instruments. Both groups are happy to help or coordinate you in order to distribute the right information. Also, we are planning some future events. We would be happy to invite you. So please receive our newsletters, and also feel free to follow us on LinkedIn, Facebook, or check out our website, technoorg.hu. All the necessary information will be there, and all of them are up to date, so please follow us and join to other events. And right now I will ask my colleagues to make your questions available for us, and we can answer some of those publicly. So we have many questions already. Let's see the first one. What is the difference between the single-sided cooled and the single-sided clamped sample holders for Unimill? They look the same.
Yeah, they look pretty similar, that's true.
Should we use the PPT just to
show?
Yeah,
maybe if we could get back to the slide and enlarge the clamped holder image. Okay, while Andras is looking for it, I will tell you. So the cooled holder is as its name suggests, it's specially made for cooled samples. So it uses a special glue for mounting the sample, and that's required for good heat contact between the cooled sample and the holder. To apply this glue, you will need a bit of skills, so you will find it probably inconvenient if you don't really need it. The clamped holder is designed for very safe sample handling. 2 spring-loaded clamps. Maybe Anders can show you on the image. Yeah, so 2 spring-loaded clamps hold the sample in position, and it's very easy to mount the sample in this holder and very easy to unmount it. So in my opinion, this is the safest holder to use. So if you don't need cooling, you should definitely use this holder. Yeah, I think, this is my answer.
Probably that's the difference. They look similar or even the same, but in principle there's a huge difference.
I should also add that these are the two holders which permit very, very low access angles or very low milling angles for the sample.
Basically zero or almost zero, right?
Yeah, basically they down almost zero milling angles. Yes.
Let's see the next one. What will be the temperature of the sample during ion milling?
Okay, it is a very good question and a relevant question for most of the samples, but it depends on many factors. So it depends on sample, mainly on the heat conductivity of the sample. Also it depends on the ion beam power. So I could say that for a silicon sample, in normal cases, the sample temperature will remain below 250 degrees centigrade for a normal case. If you have something which has a worse heat conductivity, like glass, plastic or anything, you will have a much higher temperature if you use the same ion beam power. So in these cases, you will probably use a cooling sample holder, a cooling stage, which is cooled by liquid nitrogen. And if that's not enough alone, you will attempt thinning with a lower power ion beam that is like 6 to 8 kV and a bit lower ion currents.
Actually, the primary solution, I would say, is the cooling stage. This is why we offer that.
That is.
But as we mentioned, you have access to modify all the parameters of the gun. So you can decrease the accelerating voltage or even the current. So you have many possibilities to save and protect your samples.
Yeah, that is true. Yeah, I should add that we have prepared very, very heat sensitive material with these ion guns with cooling stages. So even human bones we did with success.
Mm-hmm. Okay, short one. What is the delivery time of these ion guns? Normally it's about 8 to 10 weeks. If the shorter delivery time is important for you, please inform us and let us follow the project. In case we have the information about the desired configuration and how the project moves forward, we can shorten this delivery time for sure. What is the price of the Unimill system? It depends. It highly depends on the configuration, I would say, and all the options that you are choosing, including the cooling stage, the automated software, different kind of sample holders, many things. So please contact to our local representative, Mr. Sanjay Vaidya from Summer Instruments. I think he's more than happy to give you an up-to-date quotation. What is the usual average energy range for argon ion cleaning? So it's important that we talked about milling and cleaning. Milling is where you use high energy for the rapid milling. The cleaning is the final step. If this is the question, usually we use around 500 volts for the first step, and then if it's necessary, we can add an additional step with 300 electron volts. In some cases, if I'm correct, we use 200 and even lower energy ranges, but this is for very delicate cases. Do you agree with me? Normally I think 300 volts is enough. We have seen some cases where we needed 200 volts to reach optimal results. Right. And another question. So ideally, do you recommend having both Unimill and Gentleman in our TEM prep lab? Good question. We have many customers who have both units. It depends on your needs. So the Gentleman was optimized for this kind of final cleaning process. So if you have, I don't know, other brands or other ion mills, you can upgrade your samples. If you have an FIB, you can clean your lamellas. The TEM prep, in a TEM prep lab, I would say the Unimill is the tool what can do the whole job alone. So you can extend your capabilities and capacities with both units if you have the need for both, or you have the both application, I would say. What is the minimum temperature of cooling stage? Okay.
That depends a bit on the cooling time, but generally the stage will be the sample stage parts contacting the sample will be lower than minus 100 degrees centigrade after half an hour or 40 minutes.
Yeah. The lower the time you cool your stage, the
longer the time.
The longer the time, the lower the temperature
be,
is.
but of course it balances the ion beam power.
Sure. Another question. You mentioned a lot of other tools like diamond saw, grinding machine, etc. Can I buy these separately, or are they sold with the ion mills? You can buy it separately. They are standalone machines and they are available individually. You can have the full package including ion mill and everything, and we may give you some discount, like a package sales, but absolutely no problem, feel free. Actually, yeah, we don't have too much time. Maybe the last question is, are there any tricks to increase the electron transparent area of an argon ion milled sample? I'm not sure but the question. So the electron transparent area in case of ion milling is already a huge area compared to what you can achieve with the FIB. So basically it can be 50 times larger or even more. If the goal is to extend this area more, there are some tricks maybe. I don't know if you have
maybe I can comment on that. Yes, so you are flooding a huge, like 1 millimeter surface with ions. So if you can keep this surface really smooth, and if you can keep the hole size when the sample perforates, if you can keep the hole size very small, you will end up with a region like 50 micrometer in diameter, which will be electron transparent. For silicon, for sure, you can reach this. If you want to extend the electron transparent area, you can try to realign the sample, or you can also try to shift the center of rotation. So there are some tricks. After a while it becomes very hard, but we should really note that the area obtained by argon ion milling is usually much larger than in the case of the FIB, because in the case of the FIB, if you need very large areas, you will have a common problem which is called curtaining. So with the FIB, you can maybe thin to a depth of 5-10 micrometers. After that, surely you will have disturbing curtaining on the sample, and for sure it is very, very hard to reach 50 micrometers. I'm not saying it's impossible, but for that you will spend a lot of time and the results will be not as good. So FIB will produce electron transparent areas of a few microns ideally. For some applications it's enough, but if you need large areas for statistics, then iron milling can produce much larger areas comfortably.
Thank you. So actually, we ran out of time. So the last step is thank you very much for being here.
Yeah.
Thank
you.
It was an honor. And please don't forget to fill out the survey. What we already sent to you. That would be a great help for us. And finally for you, because our event and content could be more relevant. And also feel free to follow us on the social media. We are very active and you can get some nice information there. So thank you for being here and see you next time on our future webinars.